engineer. And what Klaus is, I think, basically famous for is discovering, anyway, some properties of certain materials that absorb CO2 when they are dry and release it when it's wet, basically. And then it's a Quaternary Ionic exchange membrane, and we can show you something what the little things look like under the microscope. And what we have done, and they use this in water treatment, and so we have these, this is an example of this membrane, if you will. Actually, these are resin particles that are embedded in this membrane. So that membrane is really about 50% active particles that will capture the CO2 and release it. So from an engineering standpoint, all I worry about is you dry it and it grabs CO2, and you wet it and it releases it. And I'm sort of charged with getting that CO2 out in some larger volumes, on the order of 1 kilogram a day or something. That's what I'm kind of working on. We do have some other materials that Alan has found from Belarus that is 100% resin, and he's testing that in this device right now to see how well it captures CO2 and releases it. This material has been chopped up, made into different forms, a rug, a fern tree, things that might increase the surface area, whatnot. This is our greenhouse mock-up, if you will. This is a single plant, and then this is a carpet of this material. It's been sitting out. It's been a little humid these last few days, so because this works on a moisture swing, it'll capture the maximum CO2 when it's dry, and then if it's very humid, if it's raining, we won't capture anything. So we have on this screen and on that screen CO2 and water content being measured in the air here. So I'm going to quickly insert this, and what should happen is this rug will essentially absorb water vapor. So it's an exchange that goes on at the ion exchange membrane, and it absorbs the water vapor and will give off the CO2. When it dries, just the reverse, the water vapor leaves the membrane. So hopefully we will see this kind of go up if this has been dry enough. If not, we can always cheat and squirt it with water. I'm sorry, the CO2, the red one should go up, and the blue one will probably suck it down. And we can also see the numbers on the top here, so if I'm watching that, we'll see that maybe go up. It looks like it might be coming up. So no cheating. Relied on blowing in. Yeah. Of course, the designs we're actually working on, Klaus has gone through a number of iterations, and what we're kind of settling on right now, and this is you heard Peter, Dr. Rittman talk about his algae, so we're the ones supplying him with the CO2. And we're going to do it using this membrane. This is our cube. It's got the membrane in sheets, and the idea is that, and these sheets are spaced at a distance such that at about 1 meter per second wind speed, it will collect CO2. So if we were perhaps in a higher wind speed regime, we could pack more sheets in here. But this is kind of the design we're working on. Then we're going to put these into a panel. Let's see if we can open that up for people. And the idea will be that we'll soak that. And you can see here that this is in fact doing what it's supposed to do. Is the CO2 going up there? Yes. Yeah. So this kind of shows
water.
Water goes slightly down.
No.
Yeah,
come on.
I
Just a
told
little
him
more
we didn't
drama.
need
We're-
to cheat.
This isn't cheating.
Oh, okay.
Cheating is opening the door and breathing in there.
We don't like to do that because then you see how little CO2 it is. But we could obviously this is great. One of the inferred limitations is the amount of CO2 that comes off is maybe up to 5%. And it depends on the structure that it's releasing into. But so if you want 100% CO2, we've got to do a little bit of work. Not a lot actually, and we're working on designs to do that, like a vacuum extraction. But for algae growth, greenhouses, we bolt right on. And the beauty of this, of course, is that it's pretty much passive. Okay. Most other, like the David Keith or whatever, he's got to ram low air in and drop hydroxide on his stuff, and then he's got to calcine it at 800 degrees C. And so if you walk up to his device, the first thing you see is a 100 kilowatt natural gas fired power plant, right, for him to get his heat. Yeah.
The question you mentioned, in order to make pure CO2 or about pure CO2, you need vacuum extraction, but that's expensive. What about putting it in water, liquid water? Then you have all the CO2 coming up.
Yeah, it doesn't seem to.
One of the things we can do is, yes, we can flood it with water. Then we can pump. If the lid is closed and sealed, we can pump the water out, and you get the vacuum that way.
That's of course another
He
possibility.
wants the CO2 to bubble into the water.
Doesn't seem to.
Perrier doesn't have that, it's not super.
It doesn't do that.
Yeah, it doesn't seem to. Not quite sure why, but we don't see that happening.
Mm-hmm.
So if you took this, immersed it, the CO2 would not come off until it was removed from the water again?
Basically, in general, I mean, you would, if you had enough time, if you left it for a long period of time, the CO2 would dissolve in the water, then it would equilibrate with the headspace gas above it.
Okay.
Mm-hmm.
You know,
But it won't effervesce.
It won't effervesce. No. But you can see from the curve on this screen, the red line is, after having seen that liquid water, is now a much steeper ramp. Right? So that's an off gas of CO2 into this box. So for every 3 ppm of CO2 rise you see on the graph, that's 1 cc of CO2 gas that's come off that little rug. Okay. So the application of liquid water accelerates that push-pull reaction that this resin has between water and CO2. So we're swinging that thing back and forth between the carbonated and bicarbonate state, and since you need water for that to happen, the faster you can get that water to those active sites, the faster the CO2 is going to come off.
Okay. Once the water's there, does the CO2 come up right away?
Yeah, we'll show you that. This is a hockey puck of this, so in a much kind of denser form than in there. So I'm going to put this in this tube, and we're going to flood it with water, and we'll measure it.
But Alan, then if you vacuum and vacuum, that's many things, because if you now say you have a tube, a high tube, and you fill it fast with water and then close it, and then you have the weight of the water, and you will then make some vacuum. Is that enough? How much vacuum? Because
yes, I mean, here's kind of the plan is we have 2 boxes. One box we fill with water. They're connected with pipes, right?
Yeah.
We fill this with water, and then we put the stuff in this box. And then we close the lid, and then we pay for the vacuum on that first box. Okay. Then we open the valve, and the water's going to flow from this box into this box halfway.
Yeah.
Right. So we get that one for, well, we don't get it for free, but it goes by itself.
Yeah.
Then we have to pump the water from this box into here. So now we have a vacuum over here, and this box is full of water, right? Then we reverse that. We let the water go from here back over to here, and we pump the water back
But
again.
can you do this by the weight of the water then? Because it has to be more or less passive.
You're either lifting the water up and down, or you're pumping it back and forth. I don't know which one is cheaper.
If you're using a vacuum pump, I think that's more expensive.
Well, I don't think you're not you're just using a water pump to pump the water, which creates the vacuum. You're not really running a vacuum pump. However,
Okay, that helps. Yeah, that
Yeah,
helps.
but-
Sure.
But you are pumping against the vacuum, yes.
Yeah,
So-
yeah, but how you do this, I don't think that's, I think that's important, in fact.
Well, and the question is whether we can pump that water without cavitating and creating
Yeah,
a bunch of nastiness in the pump itself. But once you have that vacuum and that wet resin, it's now going to off-gas CO2 and water vapor until you get a partial pressure or partial atmosphere of CO2 and water vapor. Now you can pump that gas out and you can deal with it. You can dry it, water it, compress it, whatever you want to do. And you have to pay that bill. That is true.
The beautiful thing with water is that it's incompressible.
Yes.
So you don't really make any work in the free energy exchange because that's P times delta B.
Yeah, right.
Sorry,
This is
you
right.
don't have any delta B.
No, that's right.
Whereas when you have gas,
Yeah.
But
But if you're pulling a vacuum on a water pump,
started at 420.
you know, that suction head is gonna cavitate, and that's, you know, there's
I see.
issues you're gonna have to deal with.
You're running out of ordinance.
Uh-oh.
Yeah, we're going over probably.
This software is so clunky that in order to change that, I have to stop it and restart it. It's really annoying.
10 to 1.
You put plenty of water in there, man.
Good job on that, huh?
So this wet one's probably gonna go up to about 3%, we're about 1.8 in finding here. So we'll,
This stuff is exquisitely humidity sensitive, right? And today in the lab, the dew point is about 7 degrees Celsius. So I don't know what it's like in where you come from, but here it's muggy. So that has an impact on the capacity of this material. So because it's 7 degrees dew point here, the performance of the material is substandard. So you're not seeing an optimal performance of this material, which is why this was not very impressive when it just saw the humid air inside this box, which is why this is going to go to maybe 3%, as opposed to 7 or 8%, which you would see if you were here in June when the dew point was minus 4,000 degrees. There wasn't a molecule of water to be seen anywhere. Stuff really worked well.
nonetheless, I come from the wind industry, so I designed the big wind turbines. And of course, they work best, obviously, at very high wind regimes. That's where you make your most money. The same is true for this. This will work best in very dry regimes. We're going to soak it, so we're going to get to 100% humidity artificially and rely on the drying. But that doesn't mean it doesn't work. And you can do your sums. You say, okay, I want to put it in California somewhere. Well, you go, well, what's the average relative humidity? And you do your sums and say, you know, this box that costs, you know, $50,000 will give you X amount of CO2 in California. It might give you twice as much in Arizona. So, but that's the same wind energy. You might think all the wind turbines go to the highest wind areas, and that's generally the case, but they also go where we can make the deal, where somebody will buy the power. So you need a utility that says, I want the power. So there's a lot of things that go in, and not all wind farms are placed in the absolute best wind regimes. And I suspect
Introduce it in Britain.
yeah, yeah.
That's very good.
Yeah. Yeah.